Well, let's get started. So, exciting webinar for today. A little bit of a shift from the valve and isolation focus that we've had over the last few months, looking at valve actuation and in particular electric actuators, and focusing on one hardwired simplicity outperforms digital and when it doesn't. Hosting today or taking us through this today was our very own Martin Lieber, our subject matter expert in automation. Martin is out of our Brampton office, but helps the team internally as well as our customer base across Canada and internationally, picking and selecting the right actuators, whether it's pneumatic, electric, hydraulic, and all the accessories that go with it. Martin has over 30 years of experience in the electric actuator world, working with a number of a couple of the manufacturers in his early days, and more recently in the field helping customers select the right products. Next slide, please, Martin. So as always, our goal at CGIS is to create a world without valve problems, and that does get extended not just valves, but the actuators that go with it. When we see valves, we look at them holistically, not only the component that's stopping the process or controlling the process, but there's the automation and the actuation that goes with it that can be problematic if not done properly. And so when we look at valve opportunities, it is the full package we look at, not only the valve, but the actuator as well. And we have really tried to partner with some of the world's best actuator manufacturers to be able to bring that full solution to our customer base. Next slide. Just quick introduction on CGIS for those that don't know us fully. CGIS is one of is the Canadian-based company. We have a number of partners and companies that we own underneath us. DHB is our Quebec-based distribution company. DSS Valves International, we look after the international supply and distribution of our knife gate valve. Flow Control, our Australian operation. Nova Hydromet, very specialized in autoclave, solving problems in some very difficult, harsh applications there. And then Custom Gaskets, where it all began in the 60s, manufacturing gaskets. Next slide. So as always, for those who've been on these webinars in the past, we really appreciate the questions and the participation through the webinars. So if you do have any questions, please pop it into the Q&A box down at the bottom of your screen. If it's pertinent to what Martin's talking about, we'll interrupt immediately there and try to answer those questions for you. If it's a more general question, we'll try to get to it at the end of the webinar. And if there's any other questions that pop up in your mind afterwards, Sam will be following up the webinar with an email of the recording as well as a couple pieces of collateral. But please feel free to reach out anytime, and we're happy to help. And so with that, I'm going to hand it over to Martin.
Excellent. Okay. Thanks, Braden. Yeah, so thank you everyone for joining us today. Today's presentation is a very general overview of automation and really an introduction to valve actuators and the basic current technologies available. If there's any part of the presentation you would like to discuss in detail, please feel free just to let us know, and even if you want to take something to a far greater depth, we can schedule a time to meet and work through those questions you may have. And the topics we want to cover today, not necessarily in the order as are noted, is, legacy actuators. Do they still dominate? They still dominate in tough, remote, or critical environments. And these are the true and tested actuators that were developed years ago and still have a place in the industry today. Digital actuators, where that have advanced diagnostics and things like that, they have their place also. Now, maintenance realities of the old conventional style actuator versus the new specialized type electronic actuators. We'll have a few thoughts on that. What to consider when selecting actuation for new installation or replacements. And, have a few practical examples that, outperforms next gen and, vice versa. So it'll be a myriad of topics we want to cover and just a general overview. So CGIS is a factory authorized national distributor for Limitorque actuation products, and it covers a myriad of electronic, manual type actuators and pneumatic, hydraulic actuators. Aside from that, our portfolio is very large. We have a large portfolio of other equipment that we offer. So whatever application you have, we'd be glad to look at it. And we have a team of specialized or application specialists that work with, the applications that you may be seeing now day in and day out. So it's a great team spread throughout Canada, Vancouver, Edmonton here in the East, and we'd be more than glad to support you with, any of the initiatives you're working on. Let's start right at the beginning. What is a valve actuator? Well, but very simple. It's an electric motor that drives through a series of gears, switches to open and close the valve. And there's many different types of actuators available depending on the type of the valve, the supply source you have available for the application. And it could be pneumatic, hydraulic, as we mentioned before, electrical, and they each have their place. So there's a product for just about every application you can think of. For the purpose of this discussion, we'll be limiting it to the Limitorque Electric Series actuators. So look at this guy here on the gentleman here with the yellow hard hat. He's opening and closing a valve. So think of this poor guy who's got to go out there in the cold or in a very hot temperature, who's got to open and close this valve. And he may have to do it. He may be told to go out and do it like 3 or 4 times an hour. I think that'd be very frustrating. That is why we have the actuator on the side. On the right side here, this is an actuator, also on a green valve, and it's a totally different application, but it doesn't need this gentleman in the yellow hat to open and close it. The actuator can be given a signal, open the valve, close the valve, or it can even be given a signal to say, open it a little bit, close it a little bit, several times a minute, several times an hour. Basic overview. We now want to look at a basic overview of an electric actuator, and it's a very simplistic overview. We can get into a lot of details of this. And again, if you're interested in any of those, looking at this in detail, certainly reach out and we'd be glad to do that. So it has electric motor, and that is right there. It's built into the housing of the actuator. We have a hand wheel and we have a hand auto lever. Now, why a hand wheel? In the event that there's a failure with the actuator or a loss of power or whatever it may be, the valve can still be actuated through the hand wheel. You engage this hand auto lever, and once you engage it, the motor is decoupled and the hand wheel is engaged to this drive sleeve, what they call the drive sleeve, and you can open and close the valve manually. In the control cover, that's where all your controls are, and they all look differently. So don't necessarily think that every actuator looks like this one. This happens to be the electronic series actuator that we will be discussing. The terminal bung is where all your interconnection is done with controls, with power, etc. So that just is a very basic overview of electric actuator. Now, how does the electric actuator connect to interface with the valve? I'm going to go back to this other drawing we had here and just take a focus in on this. There's a worm shaft and a worm wheel, aluminum bronze worm wheel. That interconnection there is where the motor shaft, where the motor transfers the torque to the worm wheel. All right. That is critical that's really where it all begins. And you know what? I actually have a sample here that I can show you in that. Maybe I see. Oh, here it is. So here's your what they call a drive sleeve. Okay, I'm trying to see there. Oops. Okay. And here's your worm wheel. And you can see the worm wheel here. I'm trying to make sure that you see that here. There's a worm shaft that engages on that worm wheel, and the motor is coupled to this side. That essentially is the drive of almost any actuator on the market today. How does the actuator couple to a valve? So let's take this a step further, because we kind of get an idea of how the actuator works on the inside. Now it's got to connect with the valve. And for the purpose, for this sake, we're just looking at a linear valve, a valve with a stem, with a threaded stem. There's many different types of valves up there, for which we could look at, but to keep it simple, we're just going to look at a linear valve with a threaded stem. So we have our interconnection here, which we just looked at. And there is a stem nut, this aluminum bronze. It's aluminum bronze, and really what it is a dissimilar metal from the steel, from the stem, okay? And it's an alloy of aluminum and bronze alloy, so that it is actually, the material itself is designed to be tougher than steel, but not harder necessarily. And it should run a long time, but not, but be the failure point in the end. So that stem nut is custom machined to fit any type of valve that you have. And it's contained in a base assembly, and the base assembly has bearings, so it can absorb the thrust. And it actually interfaces into that drive sleeve we just looked at. I'll show you this again. So here's your drive sleeve assembly. This is your stem nut that'll be custom machined, bore and threaded for a, oops, I'm just trying to get, there's two dogs. You can see that. That goes right in there. And this is how they interconnect. And this is retained with bearings on either side to absorb the thrust from the valve. Because linear valves, when sizing an actuator for linear valves, you need to account for not only the torque, but also the thrust it creates when you're lifting and lowering the stem. So the stem nut, this aluminum bronze, is machined, is bored and threaded to suit the valve stem, placed into the base assembly, bolted onto the base of the actuator. This whole assembly is put together, then your limits are set. That's a brief overview of how the assembly works.
Martin, could you
Yep.
elaborate on what you mean when you say your limits are set?
So a valve has an open has an open limit and a closed limit. When the valve is closed, you have to make sure that the actuator stops. There's different ways of that actuator stopping. It could be by torque if it's a gate valve, or by limit. Whichever way you do, the actuator has to be told, that has to be programmed in the electronic series, that you need to stop at this and this point.
Okay, thanks.
When it opens up, you also need to tell it to stop at a certain point. So that's setting the limits. And there's different ways of doing it for the different technologies that we'll be looking at. Let's look into the actuator a little bit, the key design features of an electric actuator. We talked about the actuator just having, cobbling together a motor with some gears. Well, that doesn't quite work. It doesn't work like that. They've been designed for a purpose, with intention of an application. And the features that are designed into a valve actuator is it has an inherent an integral torque limiting device. And the motor is designed for high torque starting loads, with typically a 15-minute duty. Before we go any further, I'm going to take us back into history. Many, many years ago, and this is where the Limitorque actuator was born. Let's put it that way. There was a guy by the name of Payne Dean in the 1920s, over 100 years ago. And he developed the first actuator. And he coined with the acronym Limitorque because it aptly described the ability of the device to limit the torque. And from this development to today is where the Limitorque actuator, this was the origin of the Limitorque actuator. This was the origin of the first valve actuator and also the Limitorque actuator that we know of today. So Limitorque really was the first developed the first valve actuator. And here's a model of, or here's actually the unit that he designed, built right here. And if you look at the technology in here, and I can see there's a spline shaft right here, the technology of how it limits the torque will be very similar. The thought process of how it's done will be very similar to the technology in the actuators, in the conventional actuators that we'll be looking at today. So Limitorque was the first developer, originator of the valve actuator. And then from there, many of the other competitors picked it up. Let's look at it from another perspective. Let's look at it from a perspective of the valve side. And I don't want you to read too much into these charts or into these into this chart that we have here. What we want to understand from this is just the torque profile of the different types of valves. And we'll take a moment here to just look at, if you look at a gate valve, okay, the 150 is just a reference point. So we're not looking at any specific torques. We're just looking at the torque profile here. A typical gate valve like this, which as you're opening creates a thrust and requires torque to open, as soon as it cracks the seat and starts lifting the disc off of the seat, the flow of the fluid will go around it, thrusting it up, okay? And it will drop off quite quickly, the amount of torque required to open the valve. You'll see the reverse when you go to close the valve. There's a steep increase in torque. So in particular, the gate valve will drop off quite quickly. And within maybe 10-20% of it opening, it starts dropping off already. Now, this is just a very, gate valves may vary depending on the profile of the disc, of the face, but this is just a very simplistic view. We'll look at the butterfly valve, the orange one here. Now, if that butterfly valve opens, it does drop off when it's after a certain percentage, around 20 to 30% or around 20%, you'll see a blip in the torque, because that's called the dynamic torque, when the fluid is flowing around the disc and there's a resistance to opening. Once you get past that point, it drops off quite quickly, similar to the gate valve. Certainly when you go to close it, you're going to have the same sort of profile that you have when you're opening it. Ball valves, on the other hand, the torque doesn't necessarily drop off as much in the mid stroke as it does for either a butterfly valve or a gate valve. So this is where you can easily size, gate valves and butterfly valves, on their initial torque, on their unseating torque. But when you think of it, a big ball valve that is always interfacing with the seats of the valve requires a higher than any of the other valves torque to get it to stroke through those seats for the whole stroke of the valve. So the sizing on this needs to be done you have to think about this a little differently depending on how long it takes for it to go from open to close. In that case, you will be sizing you'll be sizing on the torque required in mid travel. So this is just a brief overview again of the torque profiles of the different types of valves. The next topic we want to cover is factors that determine the actuator selection. Now, let's take a look at we're now looking at the actuator peripheral and environmental considerations. So always the application determines the valve. Doesn't matter. The actuator is always secondary to selecting the valve. You won't select an actuator and then put a valve on it. It's always the other way around. So it's so critical to get this right, because it impacts the type of automation that you will be requiring. In some applications where the bolt pattern of the actuator you choose does not fit the valve, you may have to incorporate it in adapter plate. And there's considerations when you do that also, because there's added space used up by the adapter plate. Now we come to the actuator. The actuator selection is based on the valve performance requirements. How quickly do you need this valve to close? What torque does this valve require for it to unseat, to seat, to run in mid-travel? And all these factors need to be addressed when selecting the actuator. What energy supply do you have available to operate the actuator? Now, some plants may just have air. Other plants may have, electricity, and we even, and maybe the electricity is not three-phase, but single phase. So all these things need to be considered in the selection of the correct automation. Actuator controls. Now, is this actuator going to open when a command is given from the control room? And they're reading, and it'll be a manual type of input to the actuator to say, okay, go closed now, or go open? Or is it going to be a closed loop feedback from, let's say, a flow sensor feeding back to the actuator saying, you know what, I'm seeing too much flow. You got to close down just a little bit so, we get this right. So when we address the application, first of all, the valve and the application, we look at all these things to make sure that the actuator that is selected is optimal for the application. Last but not least, environmental protection. There's applications where, actuators get drowned. They're down in manholes or whatever, and twice a year they get covered in water. So that's so important then that we look at the actuator that has an IP68 rating or an IP rating that is suitable for that. And it could be a very corrosive environment where you need additional coatings on the valve, on the actuator. And some of the applications that I've seen in the past I've been amazed what environments can do to the coating of an actuator and get underneath the paint and cause it to literally peel off the paint. So environmental protection, area classification is so critical. So making sure that the actuator is the actuator enclosure rating is suitable for the area classification that it's being put into. And typically, class 1, div 1, group C and D, but there's also a myriad of other environments that we need to ensure that the actuator is suitable for use in.
Martin, can we go back a couple slides? A great question came in. I think that's quite relevant to the torque profile one. And the question's around breakaway torque as a function of the torque required. And why do we need to be careful not to exceed mass when picking actuators? So that was the first question. And then the second question, or second part of the question was what type of safety factors are commonly used when picking actuators?
Very good question. So really unseating torque, if it's a gate valve, unseating torque, you would size it based on that and put a factor of safety on it. Typically, the valve manufacturer should be providing you that information. Now, again, the valve manufacturer is going to say, well, I don't know what media you're running it through. I don't know all these things. So it comes down to experience. Now, typically, there are rules of thumb, such as 1.3 is a typical factor safety that you'll often hear about, but it's really got to do with the application that it's being used in and what is what is super critical is that the sizing of the actuator does not exceed mast. So, and we can just have a, have a webinar just on sizing and selection, but ensuring that the maximum allowable stem torque is not exceeded. And if it's an electric application, you'd want to make sure that the actuator stall, and that is when when the torque switch is bypassed and the motor sees a stall condition, does not create torque, or the torque created by in that scenario does not exceed the mast condition. So again, it depends on the application, and there may be applications where you may be sizing with a factor of safety of 1.5 or 2 times even, depending on the environment. Years ago, did some sizing on a big ball valve for it was I think it was out in Alberta. It was exposed ball valve, -40, -50. We were sizing close to, I think, 1.8 or 2 on those, because what happens when the cold sets in, the ball gets squeezed, everything it shrinks, so the torque to run the valve gets a lot higher. So it's all based on the application. There are some guidelines for sizing, for factor safeties. And yes, mast is critical that we don't exceed it on the valve to prevent damage to the valve. That's what that value is. If you exceed the mast on the valve, you potentially could be damaging the valve.
Right. And I guess there's the consideration of duty cycle, especially when it comes down to your run torque. I mean, a lot of actuators, the brake torque is fairly a short period of time.
Yeah.
But then with a plug valve or a ball valve where you have that higher uh, profile requirement, your duty cycle needs to be considered as well, to make sure that the opening and closing times aren't going to exceed the duty cycle.
So, really good question. So, what typically the valve actuators, and there's all different. You can get extended duties, but typically gets 15 minutes at a 20 or 30% run. Now, different manufacturers have different percent run factors. Limitorque typically has a 30% run for the electronic series and 20% for the conventional hardwired actuators. We'll get into that a little bit in the presentation. So what that means is that for a period of 15 minutes, if you run 20% of the rated torque, the actuator will not overheat. It's really a matter of not overheating the motor, because there's a thermistor that will trip, it will stop. On applications where there's a long stroke time, you really got to be careful about that.
Right. Okay.
Hey, Martin, just for my own understanding, can you do a quick explanation of the electric pneumatic rack and pinion versus the pneumatic Scotch yoke lines there, and why they're different?
Yeah. So the electric actuator and the pneumatic actuator, the rack and pinion pneumatic, are capable of outputting a consistent torque depending on demand. Okay. So the resistance that it's encountering, it can put out a consistent torque. The Scotch yoke, I'd have to actually bring in the Scotch yoke is a little bit different. It has a parabola, or it has a unique curve here because of the construction, the piston itself acting on the yoke of the actuator. There is a slip fit on that. I have to show you a picture. We can get into that. But it's the way the actuator is built. The moment arc changes as it's going through its stroke.
Okay.
There's a mechanical advantage at the beginning, at the end of the torque
Correct.
of
Yeah.
the drive, and then it loses some of that because of the Scotch.
Correct. Yeah. And I'd have to bring in a picture to really explain that.
And then last thing I'll say on the safety factors, I think sometime, one of the things we see is that when specifications over demand a safety factor, that's where we can get into a lot of troubles with the mast. I mean, I think we often see, if it's a 30, maybe 4% safety factor, oftentimes the valve's no problem. But when we get into extreme conditions, or the specification asks for extreme safety factors, then trying to find a conventional valve that's able to withstand that higher mass requirements, you get into this state where it's almost impossible. You have to either upgrade the material of the shaft to have a higher mast number, or look at a different type of valve. But safety factors are something that we question often. Do you really need, an extreme safety factor, or is it just a nice to have? So
Yeah. I mean, really the manufacturer needs to confirm what what the maximum stall of the actuator is, so that like there are some guidelines, and typically it's 2 to 1, meaning that if an actuator is rated for, 100 foot-pounds unseating torque, then, the stall could be, 200 foot-pounds. So but really every manufacturer is different in that, and you have to be Limitorque actually provides information on the stall. It has technical data on the stall of their actuators, so that's what you go by.
mhm. Awesome. Okay, thank you.
So we talked about the actuator selection considerations, and just a side note here, I mean, there's all different ways of cobbling up actuators with gearboxes to increase your torque. This is just one example, and it's a quarter turn example, but for the multi-turn, it's no different. You can actually put an actuator with a gearbox to increase your torque. But just keep in mind that when you do that, yes, your torque is increased, but your stroke time is also increased. So because what happens is there's a reduction in the actuator RPM out at the output of the gearbox. So that's just, you weigh that over, and there's all different ways of sizing those actuators to fit the application. And typically our quarter turn size QX goes up to 1,500 foot-pounds. Anything less than that with a factor of safety, you could direct mount it. Otherwise, you're looking at using like a multi-turn with a quarter turn gearbox, and you could get very big torques values out of that sort of combination. Likewise, for a multi-turn application, you could get a multi-turn gearbox with a multi-turn actuator and have some really increase your torque output significantly. Now, we've come to the part where we want to discern between our actuators, the conventional hardwired series and the electronic series. And we may interchange some of the acronyms here, but hardwired meaning there's the individual components, the starters, the relays are all interconnected with conventional wiring. The electronic series, they do have wires in them, but they're typically looms interconnecting the PCB boards. So the components and starters, relays are all mounted on PCB boards. I'm going to show you an example right now. This is your conventional contactor, okay? And what this does is it starts the motor. It's really a relay, and each side of the contactor, whichever side is started up, it allows it to turn clockwise or counterclockwise. So this is a typical contactor that you'll find in a conventional hardwired actuator. In the electronic series, you can see it's got the contactor. Oops, I guess I got it. There you go. The contactor is here. It's mounted on a PCB board. All right. And this is a whole module. It's called the power supply to the actuator. It has fuses mounted on it, right on the board. That's a very basic difference when you get into the difference in the technologies. So when you look at this side of can you see my cursor there as I'm outlining the electrical component? Good. You see all those lines? Those are actually wires, okay? And you can actually follow those wires right throughout the control housing of the actuator. On the left-hand side, these are typical controls. This is not provided with the actuator. This is provided with the actuator, the electrical compartment. But this shows you how to interface it, typical on the left side, how to interface it with the actuator in order to make it, to control it. Now, this has a starter assembly in it. And when we look at the next wiring diagram, this is a typical wiring diagram of the electronic series. And you think, well, where are all the parts? Well, they're on these boards, okay? And these looms here, these will be looms, some wiring harnesses that interconnect the different boards. So component level, PCB boards with a lot more technology on it. That's the basic difference. We have a comparison chart here, and we just want to go through this and maybe just have some, hope you can get a little better idea on the difference of the technology. So we have we're now going to our L120, the Limitorque L120 series, SMB series. These are the hardwire series of actuators. They're multi-turn. The electronic series are the MX and the QX, quarter turn. The QX is a quarter turn. The MX is the multi-turn. So we have both multi-turn in electronic series and hardwired series, conventional technology. And we have the QX solely as an electronic series. In the past, they have made a conventional type quarter turn actuator. It's called the LY series. And anybody who's been out in the field they were around a long time, very good actuator. However, Limitorque has decided to go down the electronic venue or the electronic series on the quarter turn application. So what's the beauty of each of these? The nice part on the conventional actuator that uses a contactor like this, you just need a multimeter and you can troubleshoot this. So think of the guys who are out in the field at 2 in the morning or whatever, and they got a problem. We're not going to say the Limitorque actuators break, but we know every actuator has a problem at some point in time, particularly after they've been running a very long time with no maintenance done to them. And that's often the case. The stories we hear about the Limitorque actuators. They ran for 20 years. Oh, I haven't even looked at it. So you can go there and you can troubleshoot it. You can see where the power is going. You can see if the contactor is pulling in, when the signal is there or not. And I need to replace the contactor. Put it out, put the next one in. We're moving on. On the electronic series, with the PC board level controls, it's a little bit different. They actually have a LimiGuard software that monitors monitors the diagnostics or carries the diagnostics in the actuator, and it monitors the relays to make sure it is meeting the settings. And it actually has messages on it. Let's say, for example, I get a problem and suddenly it stops working, and it may say torque overload, or it may say my encoder is a problem, or whatever. It has a readout that tells you what the problem is. Now, always keep in mind, the service guys who work on this sort of technology, they'll say, yeah, it might be an encoder, but no, and this is no different than when you bring your car in and it says, well, my sensor, I have a problem with my sensors. The thought process is the same. Yes, it could be the sensor, but it could also be a crimped wire leading to that sensor, right? So, which is bringing up this fault. So what typically the service guys do or know is they ask, well, what's it doing? What's it not doing? What's the symptom of the actuator? And then they'll say already, okay, if this is happening and that is happening and you're getting this readout, then we know it's this, and this. So, fault detection is yes, the LimiGuard software is excellent, and any manufacturer that has that will tell you it's great. But in reality, that's great. The software is great, but you also need the experience of understanding the symptom that the actuator is experiencing. And then at that point, replacing the component is at a board level. Now, controls. On the hardwired series, the L120 series or the SMB, you're limited to really 24 volt or 120 volt control, and controlling it with 4 to 20 milliamp a loop. Also, there's features in there that you can get feedback, 4 to 20 milliamp signal feedback. The electronic series has that also, but in addition to that, you can get it with special communication boards such as DeviceNet, Modbus Foundation, etc., HART, where you can communicate with not only uh, um, you know, the 24 or 120 volt signals, but you can actually communicate through these other platforms. That's the electronic series. Now, uniquely, look at the switch ratings of the hardwired series, the L120 and the SMB, and look at the ratings here for the for the electronic series. These actuators, the hardware, were developed in a different time, a different era when electronics wasn't as prevalent. So back then they ran higher current loads through the switches to start a motor or whatever, or give a signal to start up a pump or whatever the actuator did. So the if you actually look at the contacts on the SMB, they're big solid contacts and they can carry a high current load. Meanwhile, the electronic series has a very small current load capability. The hardwired series, they're all mechanical switches, and the electronic series has electronic torque control. We're going to get into a little bit this on the next slide or so. The basic controls that you need to start an actuator are standard on the electronic series and optional because, see, the L120 was developed in a time back in the 80s, I believe it was, to compete with or for the power industry where they were actually placing the starters in a remote location in a room. So if you had 30, 40, 50, 100 actuators, you would have a panel, you would have your starter circuit in there. So you could walk into a room and say, that's the starter circuit. Oh, let's troubleshoot that. So, and it was very modularized. So it could be, that starter assembly could be located remotely. The new electronic series has it all integrally built in. However, it is much more economically priced. And it also, local controls are also an option on the hardwired series, but standard on the electronic series. One other point I want to make is that on the mechanical side, on the mechanical operation of the actuator, the SMB, which was born in the 1920s and successive generations was developed. And so after the original design, there was the S series. In the 1940s was the SM series, 1950s were the SMA. And if you look going into a plant with a lot of old equipment, you'll probably still see some of those running because back in the 1950s and the 60s and a lot of the 70s, Limitorque predominated in the marketplace. And the SMB uses angular contact bearings. And if you can see this bearing here, angular contact roller bearings, they were designed for very high thrust and the and minimal or mitigated any side loads that could be seen. You will see these on sluice gates, heavy equipment, hydroelectric dams, and that sort of thing, where heavy, where they're actually lifting heavy loads. The new competitive more actuators, the L120s, use a needle bearing style, which is very good. It's more, how can I say, more economically designed for the application, but both actuators are designed for longevity. In the application they're designed for. Just from this slide here, I just want you just to see really the difference in the technology. So the conventional technology has a switch. There's a bunch of gears right in here that turns and turns and turns, and there is a bevel gear arrangement here. Okay, the torque switch is also mechanical. You can see that it's actually an offset arm, and when this slides back and forth, it trips the torque switch. So that's the core, that's the heart of the conventional actuator. Electronic series, all right, has just one, the actuator interfaces really with one drive. And this is the encoder here. I want to show you. This is your encoder. And in this technology, it counts the number of turns and has registers, and it stores the information of where it's at in this thing. And it communicates with the main electronic board, which you'll see over here. And from there, it can, they talk to each other. This is the drive that you see right here. It slides in here, okay? And then this is retained, and it turns the encoder. This bevel gear, which you see right in here, is really the only interface to the controls. You have your switches here. You could simulate your encoders, this arrangement here with this, but this also feeds the logic that compares the motor speed, voltage, and temperature, and comes up with a decision, a torque decision, which models the torque switch on this side. So torque sensing is electronic in the electronic, is, how can I say, it's software based in the electronic actuator. And that really is the main interface. Here you have more interfaces, and it's mechanical, and here you really just have the one driving the encoder. And so the encoder is very crucial to the actuator. And if you what Limitorque developed way back was the absolute encoder. So even if you shut the actuator off, you go on site, let's say you lost your power and you went to manually close the valve, when the power comes back up, it will know that where it's located. It will know that, hey, I've been opened another 20% or 30%. So pick it up from there and go open or go close or go to a preset condition that we should be at when the controls come up. Just an overview of the different models that are offered. SMB model, this is the legacy actuator. This is the unit that, as mentioned, followed actually the SMA. I came up to the SMA in the 1950s. The SMB picked up from the mid 1965. This actuator is still available today. We can rebuild an actuator from 1965, 1968 that is an SMB. And we know of cases where they've run for 30, 40 years on applications, and they will run another 30, 40 years if they're refurbed to factory standards. And at CGIS, we are a factory authorized repair facility. We can do that. These are known for their high thrust capacity and high loads. These actuators are available with, how can I say it, very large motors and high torque, and exceeding. They have a greater torque capacity than the electronic series, and they are the lowest cost of ownership. If you wanted an application, if you have an application that needs to run 30, 40 years, you'd be looking at this. If the application requires very high loads and very severe service, and that's where you'll be looking at this actuator. Very simple. The whole housing of the actuator is either a cast or ductile iron housing, absorbs the thrust of the actuator. It doesn't have a separable base. It was designed as a whole integral unit. It's also our Limitorque's nuclear rated actuator that they use extensively in nuclear facilities here in Canada. So where do you use this? You would use it on sluice gates, on floodgates. We sell these often into the steel industry where they have severe applications, dirty applications, and need to have need operation 24/7 and work for a long time. The L120.
Just
Yep.
a quick note as Martin's going through all these, we will be sending out a slide deck. I know this is a very text heavy slide, so I'll be sending it out to everyone if you need to. Don't worry about taking notes or anything like that.
Yeah, and we just want to give a very brief overview, of the application where they, might shine, right? So the L120 is very good if you have we need competitively priced actuator, quality actuator. These units are known to run for years and years, 20, 30 years also, and we rebuild them all the time. They are, again, using wastewater, water, petrochemical, power generation. It is a good, solid all-around actuator, and it is available in both the SMB and the L120 are conventional technology. So if the guys on site like to use that sort of equipment, we got it. It's here. That hasn't gone away. And some competitors have already gone away from that technology. Well, we still have it, and it still has its place out there in the industry. The electronic series, the MX actuator, is a very good actuator. Communication protocols, as we already alluded to, it's used extensively in petrochemical and water and wastewater application, oil and gas, power generation, and you do see them more and more in power plants and cogen plants. But you see a combination of them showing up there with the L120 series, the hardwired series with remote starter panels. So again, that one and the QX are very similar. The technology is the same, and the applications would be the same. The QX is just for quarter turn applications. There are variations of these actuators that can be used for linear applications. With a linear, how can I say, a linear stem coming out of it. And we also have a QXM, so it can turn about 20 turns if you have specific applications where, it can turn 90 degrees, but it also can do full 20 turns if you have a specific application that requires, a limited amount of turns. Now, the other thing is this, another point I just want to share is that the electronic series is designed for Arctic, low temperature applications. It comes with an Arctic board. And you might ask, well, why wouldn't I want to use a conventional actuator in very, very cold weather? Well, you can. But think of it this way. The electronic actuator has less moving parts. It doesn't have a mechanical torque switch. It's done by the electronic software, the Limitorque software. And the less moving parts you have in a cold, the better. Now, the one critical thing that you need to keep in mind in cold weather applications is to make sure that the enclosure doesn't get so cold that the contactor seizes up. And this is where they actually have heaters underneath. The Arctic build will have a heater just to make sure that there's sufficient temperature in the housing, the main board, the Arctic board, so that it maintains a minimum amount of temperature. And that's where you will see failures if you don't have that, is that the contact gets so cold that the contactor components actually seize up. So that's why the electronic series was designed for, Arctic and temperatures down to -50. Ease of commissioning. Just an overview again from, just from a very simplistic perspective, ease of commissioning. Conventional hardwired actuators like the SMB, the L120, they're more difficult. You need to turn the number of turns and make sure that the switch clicks or engages when it's at the close limit, and vice versa for the open limit. The electronic series, you actually have a little communication going with it. It'll ask you a question. Are you closed now? You say, yes, I am. And then he says, and then you'll switch it into local, and then you run it open, and then it'll say, and they'll ask you the question, is this where your open is supposed to be? And you'll say yes, through the knobs, through the user interface. And so it really becomes a very simplistic exercise, and it's very user-friendly. Now, simplicity of troubleshooting, unless you're really experienced with the electronic type, know the symptoms and can read the, sometimes between what it's telling you and what the experience you've had of repairing these things, it may not be the easiest. However, when you troubleshoot a basic hardwired actuator, you just need a multimeter, you probe it, you follow the signal through, and you can very quickly find out where the fault is. User interface, well, it's very simple to, talk to the electronic series because there's literally a communication going on between the two of you while you're doing that. Meanwhile, the hardwired series, there really isn't. It's, let's connect the power, hook it all up, connect your controls, and let's see if it works. Both are very reliable. Limitorque products are known for their reliability, longevity. We have actuators, that even electronic series actuators that 20 years, 15, 20, maybe even longer. And the technology, the resilience in the technology, the software technology has increased significantly with every upgrade they've done. Repairability, both are, you know, quite easily done. The electronic series is at a component level, and you know what, you'd really have to be stocking the whole board for any repair. Perform diagnostics. Again, it's not that easy. Um, yes, the electronic actuator will tell you its faults. I know we talked about, um, um, the performance diagnostics. There are none on the electric conventional type, but you can get options on the electronic ones where you can actually see, the torque of a history of the torque of the valve. And when it comes to, heavy loads and high torque requirements, the SMB, the L120 win out in the end because they go up to thousands and thousands of foot-pounds of torque output. If you couple that to a gearbox, you can be turning you know, essentially the globe. They get very, very large. So, in closing, let's just summarize a little bit. Always, the application dictates the valve. We can't get around that. It's the reality. You got to pick the valve first. And this is something we do day in and day out at CGIS, looking at the application. If you came to us and you said, well, yeah, I just want a valve, I just want XYZ valve, we say, whoa, 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 what are you using it in? By the way, has the other valve failed or is this a new application? And we would ask a lot of questions because we want to get it right. Choosing the optimal valve for the application dictates the automation. It will always be the case. Another thought that I like to share is that, valves and automation cannot be an afterthought in a process operation. When plant is being built, this requires prioritization in a project so that at the get-go, the optimal selection of the actuated valves and control systems can be effectively implemented. There's nothing worse than trying to, rejig something that wasn't done right in the first place, particularly after you pulled wires and you did all that work. So, we're here to discuss all those applications that you might have at the very get-go. Another thought: lowest cost of ownership will always dictate the optimal valve and automation package. So when we talk about lowest cost of ownership, it's not necessarily the lowest initial price, but it will be the one that serves you the longest and really saves you money in the long run. So give that some thought. If you have any applications or you have any further questions on this presentation or any slides you want to go in detail, don't hesitate to reach out. We're always glad to have that chat and support you in any way we can.
Perfect. Martin, there's some really good questions that come in,
Yep.
so let's run on those. Can the actuators be installed in any orientation on the valves? And so I'll let you answer, and then
Yeah, and that's a great question. You know what? The Hardwired series have a preferred orientation because they're grease filled, and the electronic series are oil filled. Okay, so when you're looking at they will work, but when you're looking at, you really want, if they're at an angle, the Hardwired series, you want the grease flowing into the interface where the worm and the worm wheel meet. So you want it at the angle where this and this fits. So let's say if you don't want it on top and the grease going to the bottom, you want it like this. If you see what I'm getting at, if you're slow, you always want the grease so that gravity flows into this interface. Does
I
that
think
help?
there's also some other considerations when we look at the valve. There
Yeah,
is some flexibility, and we do have a sheet that I think we provide us often when for quotes that allow you to change some of the orientation. I mean, hand wheels, the user interface on the
correct.
digital version can often be switched around. But also a big
Side hand wheel. Yep.
consideration is the valve you're putting it on, right? Some valves wedge gates, for example, really should be up and down time and time. They don't have the packing design is not ideal for the side load of a heavy actuator off the side of it. Other valves, the DSS knife gate valve with the heavy top works has a lot more flexibility in being able to install it in different orientations. And so it's a great question and something that we should be asking and working through when we're specifying those actuators.
Yeah.
The next one is just on elaborating on the fail position, fail open, fail close, fail last with conventional and digital actuators. If you want to touch on that briefly.
Yeah, so the electronic series actuators has that feature built in on the loss of control. If you lose your supply power, we have an issue. It will not be able to do that. The hardwired series actuators do not have that option. So then what happens is there's ways to get around this. There's ways to do this, and using backups, battery backup systems to drive your actuation, and we can look at all that. So there are options, but the electronic series has a fail last, a fail close, an ESD option where if certain conditions are met, the actuator will close on its own. However, if you lose the three-phase power, because we're talking about three-phase, if you lose your supply power, it will not be able to close.
Having said that, we are working on some really cool installations using a secondary supplier that can help with spring a spring system to fail close on loss of power as well. Like I said, battery backup. So there's options and
there's all different options, and we have all different
more,
access to all different equipment available to do that.
yeah. So those ones are definitely more specialized, more engineered solutions rather than off the shelf. But Martin, with his expertise, can definitely help on any of those ones. All right. So I see that we're a couple minutes over our allotted time, so we will cut it off there. Martin, thank you so much for all your wealth of knowledge. And like I said, we're here to help. So if there's anybody that has questions that come to mind afterwards, please feel free to respond to Sam's email or reach out to any one of us or your local TSR, technical sales rep, and happy to help. But otherwise, have a great rest of your day and happy holiday season. And thanks, everybody.
Thanks.
Thanks a lot, Martin.
Thank you.